Number 44, repeat example 10.15, in which the disk originally spins clockwise at 1000 RPM and has a radius of 1.5 centimeters. So the picture's up here, guys, on the upper right. What I tried to do over here was just simplify it without the table and whatnot. Here's the disk. All right, it's traveling linearly. It has a mass of 0.05 kilograms. The linear velocity is going to be 30 meters per second. And this disk, is now also rotating clockwise at 1000 RPM. I already converted that into radians per second. All right. And the radius of this disk is also 0.015 meters. Now, what we are asked to do is we are now asked in terms of some of the other given information is in this example, but the first question is basically what is the angular velocity of the two after the collision? So after the collision, we know that the objects stick together. As it says in the question, it says it sticks. And the two objects then, once they're stuck together, rotate. So therefore, they have some angular momentum. So the best way to approach this is to consider the conservation of angular momentum. All right. So what we have here is we have angular momentum, which is denoted by the letter L. The initial value should equal then the final value. Okay. Now, you might say to yourself, and I explained this concept in the prior problem. So some of these concepts in this question, by the way, I'm probably going to go a little faster because I did a very detailed discussion on number 43. So any gaps, please check out number 43. In any case, what I'm going to do here is I'm going to take the point at which this disk just almost comes in contact with the rod here, okay? Like the minuscule, infinitesimally small second right before the impact. That being the case, I can actually then kind of estimate this linear velocity and I can estimate its angular velocity. How can I do that? Well, we know this equation that the tangential velocity is equal to the radius multiplied by the angular velocity. And therefore, to find angular velocity, it's just simply, right, this is just algebra. We need to know the tangential velocity, which is basically the linear velocity, and then divide it by the radius, or the distance that the distance of interest between the point at which the object is rotating and the axis of rotation. All right, so I know this R value, it's 1.2 meters, as it told me in the question, and then the tangential velocity is exactly the 30 meters per second. All right, so what I can do here is, again, I know I can basically translate this linear velocity into an angular velocity. So what I realize is that in the initial case, I have an initial angular velocity, all right, of this disk. Basically, I'll write, I know it might be a little confusing, but I'm going to write L sub L for the angular momentum of the linear, okay, velocity, as we just discussed. And I have to add to that now, which is basically going to be minuscule, but just for completeness sake, the disk itself over here is also rotating. All right, and therefore this also has some angular momentum to it. So I'm going to say that's the angular momentum of the disk. And that now must equal then the final angular momentum. And the final angular momentum here is the whole system taken together, because basically it's an inelastic collision. So therefore, I'm going to just say the angular momentum of the total system, okay? So expanding on these terms now, right, I can use this formula on the bottom right. I can then say that the moment of inertia for the disk, which a part of the linear part, is going to be multiplied by the angular velocity of that linear part, plus then the moment of inertia of the disk, all right, multiplied by the angular velocity of that rotating disk, and that will then equal the final moment of inertia of the total system, all right, multiplied by the angular velocity of that total system. Now it asks me what's the angular velocity after the collision. I'm after this, okay? So solving for that now, the angular velocity of the system is just simply IL omega L plus ID omega D, all divided by IS. Now, we have to, this seems simple, but now we got to expand on each of these, all right? So so now we have to think about the nature of the rotating objects, or whatever the case is. The moment of inertia for the linear part, remember the linear part I'm basically saying right before the collision actually happens, it's this disk once it makes contact with this, it's going to then, it's basically rotating around this fixed axis of rotation in this manner, where the mass is located on the periphery the whole time. And therefore, the best approximation of that is going to be the hoop about the cylinder, all right, or the hoop about a cylinder axis. So therefore, now I can expand on this moment of inertia, and I can say that it's the mass of the disk, because that's what I'm talking about, multiplied by the radius of that disk at the point of relative to the axis of rotation, right, of the entire system. Remember, I'm keeping in mind this is the linear part, okay? So that being the case, then I can multiply it now by the angular velocity. But remember, the angular velocity as I defined up here is basically the tangential velocity multiplied by r. So now I can say that is vt over r, all right? And notice what I can kind of simplify these r's if I wanted, right? I can cancel that r with one of the squares, all right? And then plus, now it's going to be the moment of inertia for the disk. Now remember, it's a disk, okay? I didn't have room to fit another picture here, but you can check it out in the OpenStax textbook, College Physics, page 359. And the disk moment of inertia formula is going to be mr squared. Remember, we're talking about the disk here now specifically. Divided, I really should be using a different letter here. This D, let me capitalize that D. Hold on one second. Just so that they're not the same, okay? It's this, then D. Okay. And then that's also going to be divided by 2. All right, that's the moment of inertia for a disk. And then that's going to be multiplied by the angular velocity of the disk. And they told that to us in the problem, right? It's 104.7 radians per second. So you can plug that number in here, right? If you wanted, you can do the actual conversion of... Actually, I'm just going to leave it as omega for now of the disk, okay? And then that all divided by now the moment of inertia of the system. Okay, so the moment of inertia of the system now, this is fun. So you have to consider what's happening. After the collision happens up here, the disk is then stuck to the rod. That being the case, there is no more angular momentum of the disk itself, meaning rotating around its center axis. There is, though, angular momentum for the disk in this direction, okay? And in conjunction with the rod. Now remember, the fixed point is right here. So I have I have one system here, but I have to break this up into two objects. Okay, I got the disk's mass that is going to make a rotation around the periphery here, which is approximated by this hoop. And then I also have to take into account that the rod is also rotating around that axis. And this rod here is going to be making... How can I do this? 1 second. No, I thought I could. Why isn't it doing it? Yeah, this program changed the functionality on me. So now this rod is also going to be rotating around a center axis. So that's approximated by the thin rod about the axis through one end. Okay. All right. That being the case, now I'm going to plug them in. So this is going to be then remember the moment of inertia of the system is going to be these two. Moment of inertia for the disk, which is equal to mr squared, plus then the moment of inertia for the rod, which is the mass of the rod, times the length of the rod squared, all divided by 3. I know I'm getting towards the bottom of the page. This whole thing is divided by 3. Okay? All right, now finally we can plug in our values. All right? So now, oh my goodness, there's like no space. So, where do I do this now? Okay, so what I'm going to do here, sorry guys, I'm just taking a minute just to see how I want to do this. I'm going to erase all this. All right, let's move this on up. And then now I'm going to plug it in. All right, so omega is going to be the mass of the disk, which is 0.05, times then the radius. I can cancel one of those radii, whatever. So this is the 1.2 times the 30 meters per second. That's then going to be plus now the mass of the disk, again, is 0.5 times then the radius of that disk itself, 0.15 squared. Oops, 0.015, excuse me, 0.015 squared, all divided by 2 times then that omega value of about 104.7, all divided then by the mass of the disk, which is 0.05, times the radius of that disk. But remember, it's about this center axis, okay? So it's rotating. I already explained that. So this is going to be then 1.2 squared plus the mass of the rod, which was 2 kilograms, multiplied by the length of the rod, which is 1.2 meters squared, and then that's all divided by 3. And here we can now plug in our values. This problem is insane. All right. Hopefully we don't make a calculation mistake now, right? Times 30. All right, plus, so I'm just plugging everything on into the calculator. So 0.05 times 0.015 squared, all divided by 2, times 104.7. And now that whole thing divided by now 0.05 times 1.2 squared plus 2 times 1.2 squared divided by 3. So I get about this is 1.74. 1.74 radians per second. That's the final angular velocity. Okay? Who's having fun? Who is having fun out there? I know I am. All right. So that's the answer to part A. I'm going to leave the answer up there at the top. Okay, let's now look at part B. I'm going to erase all this. Obviously, that's the beautiful part about the video. You can always rewind, pause it there if you need to see the work again. So letter B, what is the kinetic energy before and after the collision? All right, so in terms of the kinetic energy, kinetic energy before, okay, there's going to be two components, right? You have this disk traveling linearly, so it has a linear kinetic energy, and the disk itself is also rotating, and therefore you have a rotational kinetic energy. So the total of the kinetic energy before, right, will be the kinetic energy, the linear kinetic energy plus then the rotational kinetic energy. Now this works. This is probably going to be almost minuscule. You can probably disregard it. All right, it shouldn't make a difference, but I'm going to do it anyway. So this is then 1/2 multiplied by the mass of the disk, so that's 0.05, times the linear velocity of 30 meters per second squared, plus then the 1/2 multiplied by the moment of inertia of the disk itself that's rotating, right? It's rotating about its center axis. Its radius is 0.015. We already talked about the disk formula. So that's going to be 0.05 multiplied by the radius 0.015, and that's squared, right? All divided then by 2. And then multiplying it by the angular velocity, which was this, okay, 104.7. So this is times 104.7 squared. And then just calculate that, okay? So this will now be equal to the kinetic energy before. And let's plug in this monster. So 0.5 times 0.05 times 30 squared plus 0.5 times 0.05 times 0.015 squared divided by 2 times 104.7 squared. And it works out to be about 22.5 again. All right, 22.5. It's basically the same as the other problem. It's slightly greater, but really not by much. And that is in joules. Okay, so that's the kinetic energy before. All right, let's take this now. And let's move it, resize. So that's the answer before. So this is part of part B. All right. And then kinetic energy after. Okay. Kinetic energy after. So the kinetic energy after, all right, is basically, it's just now rotating. It's a single system that is rotating about a fixed axis here. That being the case, right, we can simply use this formula, all right? So it's just going to be the kinetic energy of rotation is equal to 1/2 moment of inertia multiplied by angular velocity squared. There's going to be 1/2 times the total system moment of inertia. Man, I wish I saved that work now, right? So let me see. Instead of deducing it all again, I already did the total system's moment of inertia before. Should probably just look it up in the calculator, but let's just try to reason it out. So it's going to be the mass of the disk, so 0.05 multiplied by the radius of its rotation, so 1.2. and that's going to be squared, and that's it for that. And then plus, now the rod, so that's going to be the mass of the rod was 2 kilograms. 2 kilograms multiplied by the length of the rod, which is 1.2 meters. That's squared all over 3. Great. And then multiplied by the final angular velocity, and that's the whole point of part A. It was about 1.74, wasn't it 0.44 or something? Yeah, 0.45, whatever. It's not really. I'm rounding now. It's 0.447, but I'll do we'll get a more exact value, 0.448, let's call it. Okay. And then just solve that on out. So kinetic energy of after the collision, it's simply going to be 0.5 times now in parentheses 0.05 times 1.2 squared plus 2 times 1.2 squared divided by 3. Close those parentheses, then multiply that by don't forget to square it. See, I almost made a silly mistake. Times 1.7448 squared. And we get about 1.57 here. So 1.57, and that's going to be in joules. Okay, let me make that a little neater. 1.57 joules. Okay, let's take this now. Let's resize this. We'll throw it on up to the top. Resize. Oh no. I didn't catch that part. Hold on one second. Okay, this should be better. Let's resize this. And that's the value after. Okay, great. That's still part of part B. And now finally part C. So let's see what we can do here. Change the color. Getting a little tired of the same color. So let's do part C. What does it say? What is the total linear momentum before and after the collision? All right, so we're dealing with linear momentum. All right, so let's talk about the linear momentum P before the collision. Remember, so before the collision happens, there's only really one object that's moving, just the disk. Okay, so we have to find basically the linear momentum of that disk, and that's pretty easy. Okay, so the momentum is equal to mv. The momentum, therefore, of the disk before the collision is going to be equal to the mass of the disk, which is 0.05 multiplied then by its velocity of 30. Okay, and so here we go. So now let's just plug it in. So basically, it's going to be 30 times 0.05, and that's 1.5. So this is just 1.5, and that will be the momentum. Kilogram, you can write in the units if you want, kilogram meter per second. Instead of writing the disk here, I'm just going to write it's the momentum before the collision. So that's all that is. Let's resize this, get this out of the way. And that's that answer. Okay, this is beginning now part C at the top. So that's for part C. And then we got to do it for after. Okay. This is still part C. So now we're going to do it for after the collision. And so the momentum after. Now, on this part, there is one system that's rotating. However, the nature of the two objects rotating is going to be different, okay? The reason why is because if you were to, I know the picture's a little tiny up there, but here's the rod, here's the ball that's stuck to it, and it's rotating around this particular point, okay? So as this thing rotates, okay, actually, let me see if I can just rotate. Now, so as this thing rotates, the velocity, the tangential velocity, is different for the disk than for, well, different parts of this rod, okay? The tangential velocity is smallest, closest to the axis of rotation, and then it's largest away or furthest away from the axis of rotation. Why is that the case? Because we already talked about this formula, right? The tangential velocity is equal to r times omega. Omega is basically constant, okay? There's no friction, so I can assume that. No matter where you are on this rod, the angular change is the same, right? For this rod to go from this location to, let's say, this location, no matter if you're at this point right here or this point, you still had to travel the same angle, Right? It's still the same angle in here, theta, whatever. But look at the distance. The distance is different. All right? So the velocity should be, the tangential or the linear velocity should be different. That being the case, we're going to use and keep in mind this relationship, okay, while we try to approach this problem. So now there's two components like I just mentioned because it depends on the distance, all right? So now so the momentum after is going to be equal to the momentum of the disk portion after the collision plus the momentum of the rod, okay? Now, we can break this down. So the mass of the disk multiplied by the radius, what am I talking about, radius? Multiplied by the linear velocity, I'm just going to call it VT, okay, for now, of the disk. And that, not equal, but plus the mass now of the rod times the tangential velocity of the rod, okay? Now, I know you might be thinking, Andrew, you just told me, here's the point of, here's the axis of rotation. Everywhere I go along this rod, my tangential velocity is going to be different, so how do I find one number? Well, it's going to be smallest here, greatest out here. It's a proportional relationship, and that being the case, we can just take the average right in the center, okay? You don't have to do every little, I mean, it's really a continuous rod, but you don't have to think about every little infinitesimally small discrete piece here. You just take the average about the middle, all right, because it'll even out. The greater tangential velocities will be balanced by the smaller tangential velocities, all right? So now, that being the case, this should be, I think, pretty straightforward. So the mass of the disk is going to be, 0.05. The tangential velocity of the disk, I'm just going to substitute in this formula, okay? It's actually, you know what? Let me just do the substitution first. So this is going to be the mass of the disk multiplied by the radius of the disk, multiplied then by the angular velocity of the disk, plus then the mass of the rod, multiplied by the, I would call, this is essentially the radius of the rod, but it's, it's not the full length of the rod. I just spoke about that, okay? So basically we'll say it's the length of the rod over 2, because we're taking the average. And then that multiplied now by our omega, okay, of the rod. Remember, these omegas are the same. It doesn't matter if you're the disk or the rod. You're both angular. Your angular velocities are the same. I can factor this on out if I wanted to simplify it. I'm not going to do that. I'm just going to calculate. So this is mass of the disk, which is 0.05 multiplied by the radius from its axis of rotation, which is 1.2, multiplied then by the angular velocity. Let's just use the value of 1.74 for now. 1.74, I'm not going to go all the way out with the decimals. The mass then of the rod was 2 kilograms. The length of the rod is 1.2 meters over 2, and then multiply that by 1.74. And when we do this, we should get our final answer. So let's do it. 0.05 times 1.2 times 1.74 plus 2 times 0.6 essentially, or excuse me, 0.6, and then times 1.74. And what do we get? We get about 2.20. All right, so this is going to be, we get about 1.9, but I use the rounded value. If you use the more exact value, it should be about 2.2. So, so giving you the final answer here, the linear momentum after the collision is going to be 2.20 kilogram meter per second. And that takes care of that, ladies and gentlemen. All right. Thanks for sticking with me. Appreciate it. Hopefully this video helped. If it did, give us a hand by hitting that subscribe button. That would be awesome. All right. And if this video helped at all too, the like button would be greatly appreciated. You have a great day.